Hi everyone, in this video we're going to take a look at how to conduct a t-test. I'm noticing that the subtitles there do not reflect what I say very accurately. That's better. So we are going to conduct a one-sample t-test. In the last video I showed you why we have a t and when we use that instead of a z, so just take a quick refreshing look at that. We will conduct a one-sample t-test, and at the end of that, I want to introduce the concept of an effect size, specifically a statistic called Cohen's d, and I will provide a separate video that goes into that in more detail later. And then I also want to give you the first look at APA-style reporting. APA-style reporting just being what the American Psychological Association expects in research applications. Excuse me. All right, so quick refresher, why do we use T instead of Z? In situations where we have a very small sample size, or if we do not know the standard deviation of the population, which means we have to estimate that using a sample standard deviation, we're going to use the T distribution. And as you probably recall, sampling distributions, they vary according to sample size. So a distribution with a small sample size, this would have a sample size of 11, because 11 minus 1 is 10 degrees of freedom. That curve is going to be shorter and wider than one with a greater sample size of 21. Eventually, though, as you get up into the hundreds in your sample size, the T distribution becomes the exact same thing as the Z distribution. Therefore, we can use this to be more conservative in our tests when we have small sample sizes or doing extra estimations. So, it's really no different than a z-test in its conceptual or philosophical foundation. The only two places where there's a difference are the places where we use those standardized scores. That's in step 2. The z-test, we use the z-table to find z-crit. And in the t-test, we just use a t-table to find t-critical. Step 3 is where we calculate our test statistic, and you can see that the z-test statistic is just the difference in means over standard error. The t-test is too. The difference is that this time we're using a sample standard deviation as an estimate rather than using a known population standard deviation. So it's really not that much different in most respects. This is the full rundown here of the steps if you want to pause and review that. Otherwise, let's just move on. The way I did this is I worked this out in a problem on a sheet of paper, and I took a snapshot of that. I'm going to provide that photo in case you want to see how it looks on a sheet of paper. But I've pasted in small samples of that here, just so you can see what it looks like when someone runs through this by hand. Anyway, I'm going to recreate the analysis that we did when we had people run up the stairs during that last day of class. In that case, what we're doing is we're looking at the population of stair climbers, specifically people who went up the 4 flights of stairs in EVALD, and we're comparing them to our known population. That's from the bowl of heart rates we have in our class. And under the null hypothesis, again, that's just assuming nothing's changing, we would have to say that the null hypothesis is that the mean of stair climbers would be 70.08. Here, the alternative, which is what we're interested in, would be that it is not 70.08. Okay, the next thing we're going to do is set our criteria. Now, with the z-table, what we did is we just divided our alpha in half and looked up the value here. The t-table is a little bit different, so I'm going to step away from this for just a second. So here's a t-table, and we need to do 2 things. First, we want 0.05 split into 2 tails. So that says alpha for 2-tailed test, 0.05. And then we need our degrees of freedom. In this case, we have a sample of 5 individuals. 5 people minus 1 is 4. So I see where those two connect, and I see that my critical value of t is 2.776. All right, so let's take that back here. In step 2 then, what I did is I identified a critical value of t, 4 degrees of freedom, is plus or minus 2.776. So I sketched that over here, marked it off. Of course, the average t-score is 0. All right, so step 3, this is where we do our calculations. And because we need to find our sample standard deviation, there's going to be a couple extra things to do here. So basically what I did is I just I had something like a cheat sheet here where I know that my test statistic looks like that. In order to get my standard error, I'll need standard deviation. So how do I find standard deviation? Well, I know I need some squares, and I need this formula right here. Okay, so let's go to the next screen. All right, so here I'm just going to show you kind of how my calculations worked out. The first thing I did, I knew I'd need to start here with sums of squares, so I need the sum of squared x's and the sum of x squared. So I made this table right here. And I've been making a lot of mistakes calculating today, so I kind of cheated. I went into Excel and I typed in my data and had Excel sum those up. So the sum of x is 480. X squared is here, sum that up. Okay. And then I scribbled down on my paper here and finished my calculations for sums of squares. So I found my sums of squares is 664. Next, I plugged that into this formula. So sums of squares is 664. N minus 1, that's my sample of 5 individuals minus 1. That reduces to 166. I take the square root of that. My standard deviation is 12.88. All right, so now I think I'm ready for this. To find my test value of t, first I need the sample mean. Well, the sample sums up to 480 divided by 5, that's 96. The population mean, that comes from our bowl. So we measured that in class, that was 70.08. And then I fill in the bottom half of that number right there. So again, my sample, this right here, has a mean of 96. The population, which is our bowl, that was the resting heart rates from class. Standard deviation, which I just calculated down here. And the square root of n, that's the 5 people in our sample. Our test statistic then comes out to 4.5. All right, so calculations are done. There we go. All right, now the very last thing we have is the decision. And the decision, we have to decide if we reject the null hypothesis or not. And I'm going to take this number right here and compare that to our critical value of t. Okay. So I'm going to use this right here. Notice that 4.5 is well above 2.776, which was our critical value. Because our test statistic is so much higher than our threshold here, our cutoff score, I'm going to reject the null hypothesis. And I don't know if you can see it with the subtitles, but I've scratched out the null hypothesis down here. So we're going to reject the null hypothesis because our test statistic is far greater than our critical value. All right, so again, I have provided an attachment in Moodle that shows you just this whole sheet of paper at once, so you can see how it looks when you do it by hand. Now I want to turn to what this means. It's pretty, it can be kind of complicated sometimes, so I'm just going to go over this in this video, then in another video, and we'll do this each time we work through a sample problem, and hopefully it starts to make sense. Basically, when I see the results of our test, I would write it out like this. In APA style, again, this is the American Psychological Association's requirements for statistics. I see that our t-test is 4.5. This is our test statistic, not the critical value. And this p is less than 0.05. That says our probability is less than alpha. All right, so what does that mean? Well, we refer to that p there as a p-value. P-value is less than alpha. And the decision can be described in a lot of ways. A complicated way of thinking about it is that based on the central limit theorem, if we made a confidence interval and we were taking samples over and over and over again, only fewer than 5% of samples of 5 would have an average anywhere near that. Okay, so it's telling us that that is a pretty unusual t-value to get. It's a pretty unusual sample mean to get if the null hypothesis is true. Makes me think that something probably happened. Another way to describe that is with the word significant. This is statistically significant, meaning that this isn't just randomly different. This is something pretty noticeable. It's also called a statistically significant difference or a significant difference. That's how significance get used. And ultimately what this means is there's likely to be something going on rather than just random sampling error. With random sampling error, you get t's up to 1, 1.5, even 1.9 sometimes. It's pretty unusual to get a t-value of 4.5 just by haphazard sampling. So something's probably going on. But here's the important thing, and I realize that this is going to be covered by subtitles now. The question down there is, but did something interesting or important happen? Statistical significance only means this. It does not mean that this is something major or important. Significant just means it's probably real. All right, so we need to consider the limitations of our tests. We know that we are likely to have a real effect here. The z-test says that we have significance. But what I know about t-test is that z-test and t-test both result from two different properties. I'm going to give you a full explanation of this, but bear with me for the quick one here. The two things that affect the z-test or the t-test are, first of all, the size of the distance between the means. We talk about that as the size of the effect. So think about it. This number was 96 in our study. That number was 70 in our study. That's a pretty big distance. How big is it? Well, the other thing is that it's based on the number of people in your sample. If that's a big number, the denominator gets pretty small. The curve gets really skinny. So that also influences it. Now, what do we really care about? Do we care about, can we get a big sample, or do we care about, does our manipulation cause some change? We actually care about this. So, once we have statistical significance, and we know that this is probably a real finding, then we try to do this measure of effect size. And an effect size, then, is a follow-up. It says that, okay, if we have a difference, let's see whether this significant finding is due to a large difference, not just a large sample size. Cohen's d is the most commonly used one for z and t tests. It was developed by Jacob Cohen in the 80s, and he basically removed the standard error, which gets rid of the effect size, it keeps the effect size but gets rid of sample size. And I'm going to have to show you this again later. In general, after going through a couple thousand articles, we find that about a absolute value of about 0 to 0.2 is small, 0.2 to 0.8 is medium, 0.8 up and large, 8 and up is large. So, to conclude, I calculated our Cohen's d and it's 2.01. That's pretty large. 0.8 is large, and we are 2.5 times that. So our Cohen's d in this case is very large. So not only do I know that we have a reliable finding, statistically significant finding, but this is probably a really meaningful difference that's going to be important to people who need to know about heart rates, maybe athletic trainers, physicians, things like that. So that's it. That's our first run through an entire t-test. There'll be more later on looking at effect sizes, followed by how to read about t-tests in journals.